Morning, everybody. Congratulations on surviving the fog, right? Seems to be thickening even more now. Let's see. Today, we're going to try and finish chapter 18. I don't know how successful we're going to be. It's going to come, it's going to hit you like a 2x4 today. We've got new physics, we've got vectors, we've got multiple dimensions. My advice is hang on for the ride here, right? Okay. It's gonna be wild, and you're gonna be overwhelmed, and it's gonna be okay, because as you work through it, it'll start to make sense. The V word is very much in play today, right? So we've got to try and remember that. But before we do that, let's do a quiz. Let's do a quiz and see what you remember from Tuesday. Forces, right, have to be equal when two things are interacting. We can't forget that little piece of information. Okay, so how do we use Coulomb's law in a mathematical or problem-solving context? Okay, so this problem's got an arrangement of some charges, and they want us to find the force on only one of the charge, right? Charge 2 up there, okay? It's the one on the y-axis. So we're going to try to laser focus on charge 2. Does charge 1 experience a force? Yeah, sure it does. Does charge 3 experience a force? Yeah, they're all charges. They're all near each other, right? But the question wants us to only look at charge 2. Now, that's what our answer is going to be, but we've got to track the influence of the other charges. And force is a vector. And so what we're doing is a vector addition problem. Our general strategy here, before I even write down any math, is to find out what the force on charge 2 is because of charge 1. Oh, I got to look at my notes because I can never remember the order of the thing. Force, okay, yeah. So, we're going to find the total force on charge 2. And we're going to do it by first finding what the force is on charge number 2 because of charge number 1. In other words, we are only going to look at this pair. We're going to ignore charge 3 for just a second. We'll calculate that force, and then we'll come along and we'll do this pair. And why do I have to do it pairwise? Why do I have to just isolate pairs of particles? How many charges are there in Coulomb's law? Just only 2, right? Okay, so you got to do them only in pairs, right? And then at the end, we can add together their influence because that's how vectors work, right? So that second vector, it'll be, again, this notation here says the force on 2 because of charge 3, right? Okay, so that's, in my class when I taught a problem-solving method where we strategize. We come up with a broad idea. We're not trying to get into the mathematics right away. We're not solving equations right away. We're mapping out a procedure, and then we visualize, get a picture in our heads. We strategize and try to map out a procedure. We then do it, right? We actually have to run the math, okay, and then we check it. So we're right now we're visualizing and strategizing. They've got a picture here. Let's do a little bit more visualization because we're going to find the magnitude, right? Oh, I forgot there we go. Over R squared. There's our magnitude, right? And that would be, charge 1 and charge 2, okay? So we can just calculate, we can toss that in a calculator, we'll find that. We'll do that in a bit. But we've got to be able to handle, right, these vector directions. So this is where we fall back on our knowledge of opposites attract, likes repel. So what do we got here? Let's see, charge 1. What kind of charge is charge 1? It's a positive charge, right? It says 2 microcoulombs up here, right? And then charge 2, what kind of charge is it? It's a negative charge. And charge 3? Also a negative charge. I like to put it on my diagram just so I can remember just what the heck's going on. So if I wanted to look at the force that exists on charge 2 because of charge 1, what direction would it be going? Remember, there's really only 2 directions, towards and away, right? Okay, so they're opposite charges, positive and negative, positive on 1, negative on 2, so which is the direction? Towards. And the towards direction in this diagram, in this particular setup, is pointing down like that, right? We'll map this into x and y later. But I just want to do this high level, working with the concepts of Coulomb's law, right? To be able to get this set up correct. Okay, let's look at the other 2, just while we're here in the visualization step. Q2 and Q3. What direction is that one going to be? Away, because they're both negative, right? And so the away direction from charge 2 is something up like that. Okay. We got lots of options now. Should we just go find the magnitude right now? We're going to need it, right? So if we're going to add 2 vectors together and they both have x and y components, what do we do? Like, what's the process? All the x components got to get together, all the y components, right? So we've got to find the x and y components of each one of these vectors. But before we do that, we need to know like what the magnitude of F21 is. And we can get that from Coulomb's law. So let's do that. This is F21 right here. We'll just do it in the picture, right? This is F23 right there. Sorry, the writing is so small. So let's do F12. Here's the magnitude of F12. This is not the vector yet. K. What's K? The number, right? 8.99 times 10 to the 9. I usually write it as 9 times 10 to the 9. Okay, charge number 1. What's the charge on charge 1? Be careful. Well, we're doing absolute values, right? Okay, so it doesn't matter if it's positive or negative. We're just tossing numbers in.
Are we looking for F12 or F21?
Yeah. The 2-1. Sorry. See, what I did is I reverted to college. See, it's burned into my brain, and the book does it what I consider backwards, but it's okay. So, yeah, charge 2. What's charge 2? It's 4, but do you see how it says microcoulombs? Always work in standard units. In other words, if it's written as a microcoulomb, when we go to write this number down, we're going to write 4 times 10 to the minus 6. I don't like putting my units into my number calculations because it confuses me, but you are more than welcome to put the units in if it helps you, right? But where did that times 10 to the minus 6 come from? That micro right there. It literally means times 10 to the minus 6. So make sure in your calculate, because if you left it all in microcoulombs, but the force constant is written in coulombs, now it's just going to get all confused and you're not going to have the decimal points in the right places and it goes bad. Okay, now what do we write down for charge 1? It's 2. I'm not writing the point zeros because I'm lazy. Times 10 to the minus 6 because it was a micro, right? And then we divide. Uh-oh. What are we going to divide by? It's not 1 square. Well, so keep guessing. You'll get there in the end. We need the distance between those two. This is a special kind of triangle. Does anybody remember this triangle? What are the angles?
45, 45, 90.
It's 45, 45, 90, right? So this is 45 degrees. This is 45 degrees. And you can do it the long way by doing 1 squared plus 1 squared square rooted. Or you can just remember that it's the square root of 2 times whatever the length of one of the sides is, right? So this length is the square root of 2 down here. Okay, so in the denominator here, I'm going to write the square root of 2 squared. Yeah, you can just do 2 if you want, right? But in the future, if it's not so easy to see, like, you know, you have a pattern to follow. Okay, according to my notes, which could be wrong because this is a number. And how well do numbers and Mr. Balogh get along?
Decently wrong.
No. I hate them and they hate me. This is what I got. If somebody wants to check that, you're more than welcome. Otherwise, it doesn't really matter because it's just a number. All right. I really shouldn't say things like that. That's what you got?
Yep.
Okay, good.
Yeah, tell that to the bridge builder when it collapsed.
Well, that's engineer's problem, not my problem. Okay, 9 times 10 to the 9. Okay, so now I'm going to do F23. I'm just going to find that magnitude, right? Okay. So same process, but for the first charge, what charge are we putting in?
4 times 10 to the -2.
It's charge 3. Did I write it? No, yeah, it's charge 2. So we're still writing 4 times 10 to the -6. But then what is charge 3? 6 times 10 to the -6. And it always feels a little bit awkward that we're not using the signs, but where did we use the signs? Yeah, when we did the towards and away. Okay? And Coulomb's law is a magnitude only. Don't be putting positive and negative signs in there because it'll mess you up later. And then we got square root of 2, right? Because, again, this problem is like nice and symmetric, and so that's square root of 2 right there. All right. And the number is different, and I got 0.108 newtons. Okay. So we found the magnitudes, right? Can we just go ahead and add those two numbers together and be done? No, remember, these aren't the vector. This is just what we found, right, was the magnitude of this one and like the length of this one, right? So now we need to find the components of those two vectors. The way I do this is I draw little pictures, right? What I'll do is I'll say, okay, I know that F21 is doing something like that, right? And I also know that there's like a 45-degree angle right there. So for the x component, F21x, what am I going to write? Those of you that have me before are in trouble if you don't answer right away. Touching or not touching? Is the x component of that vector touching that 45-degree angle? No. So it's sine. Okay? If you don't know what I'm talking about, you can come to grasp and I will teach you touching, not touching. But we're going to do the magnitude, 0.036 sine 45. I mean, luckily here, 45 degrees sine and cosine are the same number. But if you get a different one, it'll be nice to know. 0.036 cosine 45. And now we got to go calculate that. But we should be careful now with the directions, right? The x component, which way is it pointing? Yeah, right. This is down in the third quadrant, isn't it? So negative, negative. So minus 0.025. And this one's going to also be negative 0.025. Again, 45-degree angle. And I'll put the minus signs here just to make sure I've got them all. Okay, and then for F23x and F23y, let's see, that picture, what quadrant is F23 pointing into? Second quadrant, right? So our 45-degree angle is sitting right here if we want to do some geometry. This one looks a little bit easier. So the x component, positive or negative? Negative, good. Y component? Excellent. So then we use the magnitude, 0.108. And x component, technically sine or cosine? Is the angle touching the x component?
Yes.
Yep, so cosine. And then 0.108 sine 45. I got 0.076. Okay. For those of you who haven't had me before, have you noticed that we transitioned away from physics and we've just been doing math for like the last 3 or 4 minutes, right? Everybody wants to skip that physics step at the beginning because it's hard, it requires thought, it's not like algorithmic, you can't just chuck things in and like get numbers out, right? Which is the easy way, I guess, to do math. Don't overlook those first steps of thinking about what direction the force is pointing and like what quadrant things are in. That's vital for being able to make it through the problem unscathed.
How do you determine which quadrant to use?
Right, so should we look at 2, 3 just as an example? Okay, so what I do is remember a vector can get picked up. Like this vector right here, I don't have to keep it drawn in that location. I can move it over here. As long as I keep its magnitude and direction the same, it's the same vector no matter where I put it, right? And then what I do is I just draw or imagine a coordinate system right there with the vector at the origin. And now I can see which quadrant it's pointing into. It's a really good question. Did I help, or do you need to see it again? Let's do it again. Let's just do it with this one, right? So there's the vector. So I can just pick it up and put it right here. And then if I draw a little miniature coordinate system, which quadrant is it pointed in? Right? So now I know it's negative, negative. I like to take it out of that initial diagram up there. That initial diagram can get really busy, right? And so I like to just that's why I draw these little pictures off to the side, right? Okay? And I just draw the vector, maintaining its direction and magnitude. Sketch. It doesn't have to be accurate. And then I draw my coordinate system. And then okay, I know what coordinate I'm in. Yeah.
F23x, shouldn't that be a negative 0.076 Newton?
Yeah, thank you. I just didn't carry my sign through. You mean people forget to carry minus signs through in their calculations? Okay. Now what do we do? Again, we're trying to do this. It's right at the top of the screen. It's my guide, right? It's my lighthouse. It's telling me where I'm trying to be, right? But do I have F21 yet?
No.
Well, yeah, I have its x and y components, don't I? Do I have F23? Well, sure do. I've got their composed. So how do I add them together?
Square root.
No. How do I add vectors together? I already asked the question today. X and x, y and y, right? So that means the master equation, the master vector, F2's x component. Boy, this stuff is hard. It's just hard. Okay, is going to be negative 0.025 plus a negative 0.076. I got negative 0.101. So what is F2y's component? What two things are we putting together here?
Negative 0.025.
And?
Positive 0.076.
There we go. 0.051. Okay. So what do we, just right now, what do we learn? Where is F2 pointing? It's negative x, positive y. That's got to be second quadrant. And I'm going to kind of look at that. I go, okay, well, F23, right, is 3 times longer, right? It's 0.108 versus 0.036. So does it make sense that my answer likely will end up in the second quadrant? I like it. If I gotten plus plus here, pointing into the first quadrant, I would have started getting worried that I was doing something wrong, right? Okay. All right, so there's the components. Now, how do we find the magnitude of that vector? Square root. Are all of the bad feelings from 2a coming back now?
No.
Yeah, for most people they are, Brandon. Square root of 0.101 squared plus 0.051 squared. Why did I drop the negative sign?
We don't like that.
It's squaring everything. Just gets in the way. Stupid negative. Okay, 0.113 newtons. Okay, that's the magnitude. What's the angle? This is where we have to use the tangent inverse, which is always out to get us because it never knows where it is. 0.101, and which one's negative? This one's negative, right? So I got negative 26.8. But if you put that in a YD plus, it's going to yell at you.
Yeah.
Because that negative, okay, remember, what is that when the inverse tangent tells you negative, what is it trying to say? No. It's a rotation direction from the x-axis. Tangent, positive tangent, inverse tangent, is telling you to rotate like the standard way, counterclockwise away from the x-axis, either the positive or negative x-axis. And so therefore a negative angle is telling you to rotate which way? Clockwise. So this is saying go 26.8 degrees clockwise from either the positive or negative. Again, tangent can't tell. The only way we can tell is by looking at where this vector points. We know that this vector points negative x, positive y. So where does this vector end up? Second quadrant, somewhere up here. So that negative 26.8 must be in here. Again, rotating clockwise from the horizontal. Okay. And so what is the actual angle as measured from the positive x-axis? It's 180 plus a negative 26.8. The other thing I remember to do is like, if you, and by the way, the reason this feels like it's going fast is because this should all be review. What's the only new thing on the screen? Coulomb's law, right? The rest of it, all of these vectors and their forces and everything, that's all physics 2a stuff. But what I do when I'm thinking about inverse tangent and I'm worried about where it is, first of all, I draw a picture to see which quadrant my vector's in, okay? But the short sort of version is, what do I add?
180.
Or, 180 is not the only answer. What do I add to my angles to make it work? First quadrant, you add 0. Second and third quadrant, you add 180. You're always adding. You're going to get a negative angle, right? Which will work itself out for the second quadrant, right? Get a positive angle, work itself out for the third quadrant. What do you add in the fourth quadrant? 360, right? So when you're working with inverse tangents and you get an angle out, make sure you know what quadrant your vector's in. And if it's in the fourth quadrant, what are you going to do with the answer that tangent gave you? Add 360. And you'll get the angle measured from the positive x-axis. If your vector's in the third quadrant, whatever angle it gave you, what are you going to add?
180.
Okay? So this is negative 26.8, but since it's pointing in the second quadrant, I'm going to add 180, which gives me 153.2 degrees. So there's my answer. Magnitude and angle from the positive x-axis. Guys ready to go home yet? No. Yeah. No, come on. This is bad, right? This is horrible, okay? But this is the real deal when it comes to how charges like interact with each other. They experience forces, and those forces can be calculated, and we can do stuff with those forces. And we're starting at like a very fundamental level talking about charges. Are you ever going to wander upon a situation where you see three charges in an isosceles triangle? No, never, okay? But where are you going to run into charges? Everywhere all the time, right? Cellular metabolism, right? There's charges on either side of a semi-permeable membrane, right? And setting up those electric potentials so that you can get energy flow, okay, through that membrane and so on and so forth. All the potassium channels in your brain and neurons and blah, 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 right? The universe is a beautiful, wonderful, complicated, simple place. It can be all those things at the same time, right? And charges know what to do, but as far as our human understanding of what they're doing, how they're doing it, well, we have to map that onto Cartesian coordinates and simple problems like this. Because what we're going to be doing for the next 8 weeks is building towards more complicated arrangements of charges. But as we do that, hopefully, back up. If we had to do this with 4 charges, how much worse does all this math get? If we have a 4th charge, then we have to do another Coulomb's law, and now we're adding 3 x components and 3 y components. What if it's 8 charges? What if it's 25? What if it's trillions of charges doing something, say in a wire, as electrical energy moves from PG&E to your house, right? Like, this way of doing it becomes very cumbersome, doesn't it? And so what we need to do is we need to strike out and try to come up with ideas that models that are easier for us to do faster, okay? And that's what we are going to do now. We are going, so Coulomb's law is the law, right? It's the fundamental force that governs interactions between particles with charge in our universe. But what we're going to do is we are going to abstract, we're going to take a step away from that sort of fundamental thing, and we're going to try to simplify by making an idea and seeing if that idea has predictive power. The idea that we're going to conquer is something called electric field. And this comes straight out of the mind of Michael Faraday, who you're going to hear a lot about, but I don't have time today to really do justice to the genius of this man. Let me just tell you this. This man is my hero, okay? He went from a nobody, not a bookbinder actually, okay?
He was a bookbinder.
He was a bookbinder. His dad was a blacksmith. But in a class-conscious society in 1700s England, he went from an absolute nobody that would have gone nowhere to being the preeminent scientist of the British Empire. And he did it without knowing math. What I'm about to tell you comes straight out of the mind of Michael Faraday. And was he a genius? Actually, no, I don't think so. Not in the way that we think of like Einstein as a genius, right? Kind of thing. But Faraday had a type of genius, which was the ability to visualize things and see things that weren't there. And one of the things that he saw, that he invented to try to come to grips with a lot of this very complicated ideas of what charges and stuff are doing, is this concept and idea of the electric field. Others would come later and formalize it with mathematics and the math I'm going to show you today. But the idea of the electric field is a really, really powerful one to kind of help us simplify and take a step back. What do I mean by that? Coulomb's law, we'll just write it down again, right? Q1, Q2. Can I stop writing absolute values on this? I'm just tired of wasting electrons on it. There's the magnitude of Coulomb's law, right? Okay. The electric field would, after Faraday sort of came up with the idea, others would formalize it, is the force from Coulomb's law divided by something we call a test charge. Like a sample, like a this charge, this test charge, we're gonna move it around in space, and we're going to be able to measure what the electric field is depending on where this test charge is. But here's the real kind of kicker to this, right? For a single charge, let's say it's just like a positive charge just sitting here, okay? We could put the test charge. Here's our little, so we got a big Q, right? That's causing something to happen, and we've got a little q. Now, does that little q experience a force? Yeah. By the way, test charges are always positive. So what direction would the force be on this test charge? Away, right? So what Faraday imagined was a pattern of forces that existed around charges. So if we move this test charge around again, we kind of did this yesterday. Like if I put it up here, which way is it? It's also away. So in Faraday's imagination, he thought of a pattern that exists around this positive charge called the electric field. This pattern pointed away from the positive charge, and it spread out into space in all directions. And here's like the key simplification that Faraday's genius allows to happen. We don't need the test charge to be there at all. The electric field exists because the big Q is there. Now, this idea isn't too different from another idea that we never taught you about in Physics 2a, but you've heard about before. And that's the gravitational field. So what's the gravitational field of Earth? Like, what does it do? Right? Okay. Which way does the gravitational field point?
Towards the center.
In, towards, down. Okay. But it points like inwards towards the planet. Do my keys need to be here in order for the field to exist? No. It doesn't matter if it's keys, an elephant, my cup, whatever, right? Okay? The gravitational field of the Earth exists. Why?
Because the Earth exists.
More specifically, it's because the Earth has mass, right? Okay? So why do electric fields exist?
Because they have a charge.
Because things have charge, right? And the electric field of a point charge is the force, K, in this case, big Q, right, times the test charge. Those are the two charges in Coulomb's law, right? Divided by the distance squared, all divided by the test charge. So mathematically, what happens to the magnitude of the test charge? Goes away. Which means that the electric field of a point charge is just K times whatever charge is causing the field to happen, divided by how far away you are from that charge. The simplification here is that we have removed one of the charges. The test charge doesn't matter. Electric fields, which are real, the forces that exist between charges are very real. The pattern of forces that exists around a charge is real. What Michael Faraday did that wasn't real, and again, kind of a part of his imagination, was that he thought of the electric field as these lines. He actually initially called them tubes, okay? These tubules that connected charges with each other. You have to understand, Michael Faraday came to his knowledge and his learning in an age when scientists were still very skeptical of something called action at a distance. Newton was the first person to really suggest that like the moon and the earth are not physically connected to each other with like rods or strings, and yet the earth can pull on the moon. That's in the mid 1700s. Michael Faraday is coming of age in the early 1800s, and science is still wrestling with this, how can things influence each other if they're not like physically connected to each other? Nowadays, we're fine, like Wi-Fi, whatever, right? We're cool with this whole, yeah, magnets can push on each other, they don't have to touch, and blah, blah, blah. But Faraday was kind of insistent that no, all charges are connected to each other. There's these little Ethernet cables that connect them together, right? So that they can tell each other where they are. Modern physics believes that the way charges know where another charge is through photons, but that's getting to the end of physics 2b. So Faraday's sitting here, like, imagining, right, these lines. We call them lines nowadays. We don't call them tubes anymore, okay? And the lines had rules. He developed a whole system of rules about what these lines did. Electric field lines start on positive charges and end on negative ones. So they have a beginning and an end. The number of lines that you see in a picture is proportional to the strength of the charge. So if I got that picture right there of that positive charge, and I come over here and I do a negative charge, right? But I only draw half the number of field lines. Now, why does the electric field point towards a negative charge?
Because they end at a negative.
Because the field, good, right? You got rid of this whole towards and away and force thing and went immediately towards the rule. The rule is the lines have to end on a negative charge, right? So they have to be pointing in towards that negative charge.
So then, if these are acting on each other,
Okay, yeah. These are in separate universes right now. I haven't drawn them together. I should probably... okay? They're not influencing each other yet, okay? But because this one only has 4 lines on it, and I drew this one with 8, what can you tell me about the relative strength? Which one's bigger? The positive. And it's twice as big because there's twice as many lines, right? And there are some other rules. You don't have to worry about any of the other rules. But this visual way, right, of seeing how charges influence each other becomes very, very powerful because of that situation that you just said. Well, what if they're together? Okay. So here's my plus Q. Here's my negative Q. If I start a line on positive Q and it's just heading perfectly horizontally, am I breaking any rules if it terminates on the negative Q? No, because I started it on a positive and I ended on a negative. Okay? Well, what about a line that starts kind of going up like that? It's gonna, shouldn't there be another line that's coming down into the negative? The line kind of wants to take the path of shortest distance that it can, okay? The other rule you need to be worried about is a very important one. Electric field lines are not allowed to cross each other in space. They can't tangle, they can't intersect, they can't cross each other. So if I had a field line that was coming off down here, would I draw it going like this? No, because they cannot cross each other, right? So this one probably, now, it can be difficult to like draw these pictures if you don't have a lot of practice at it. We're actually going to do a whole lab where you're going to practice drawing. You're going to have to bring crayons, by the way, because you're going to need different colors. Okay, so we'll get there. We'll get there. Okay. Now, okay, what about this one that's coming off the back here?
like if they're equal, then it
Do I just draw the whole big circle? No. What I do is I let it go to infinity, and at infinity it wraps around and comes over here. Infinity is a kind of a handy place, right? So I can just send some of my things off like that as long as I bring them back. Now this of course, because all the lines are equal here, right? The number of lines coming off the positive and the number of lines going on to the negative, I know that the charges are equal.
So that's like, so let's say the positive has more lines than the negative.
It would have more charge.
The ones that go out at infinity are just assuming that it connects to another charge.
Somewhere else, yeah.
And then same thing with.
This brings up a good point that we don't have time to talk about, but I'm just going to mention this. Infinity is a really handy place to just put stuff that you don't want to worry about. your taxes, your boyfriend, whatever, right? Okay, just put it at infinity, okay? In physics, infinity is actually closer than you think. Like for an electron, it's about a meter away, okay, right? In all practical purposes, okay? But infinity is also like the perfect grounding spot where there's neutral charge. It's where field lines can go to die. Like it's just a handy spot, okay? But even more powerfully, if we were to drop, say, a positive charge, I don't know, right here, could you predict the path that that charge would take if we let go of it?
Yeah, it would be along the,
Yeah, what's it going to do?
follow the line.
It's going to follow the lines, right? This charge will go like this to get to that negative charge. Why doesn't it just go like,
You can't intersect the...
well, it's a physical particle. It can cross lines. But we need to take into account that it's going to get pushed away from the positive charge first before it gets pulled in, right? It's closer over here. If we had to do all of that with Coulomb's law, we'd have to map out an infinite number of points to see which way the vector directions are all pointing. That's insane. With Faraday, you're able to just look. Positive charge right here is going to go here. Done, right? Like I just know the path the charge is going to take by looking at the field lines. How much math have we done in the last 5 minutes? Hardly. Okay, does that count? Maybe, I don't know, right? But like the power of this visualization is staggering. It changed how physicists thought about charges. It brought them into this field theory, okay, that we use to this day. Now, of course, nowadays we know that Faraday's tubes don't exist. His lines are not real physical lines that connect charges. So the lines aren't real. Our visualization, our abstraction of an electric field is not real. But are electric fields real? Absolutely. And so we still use Faraday's imagination because it is just that powerful and is able to help us do things very quickly that otherwise would take supercomputers, right, to figure out. Okay, what happens if I drop a negative charge right here? Just go opposite the field lines. Negative charges go opposite the field lines because field lines are defined by what positive charges would do. Okay? All right. I'm run out of... Can I duplicate? Yeah, I can duplicate this. Okay. So let's do... hey, Michael. He's just hanging out. All right. So let's do a positive charge right here. And a no, we did that. Let's do a positive charge right there and a positive charge right there. Just see what happens. I'm actually taking too much time on this, but you guys are asking a lot of questions. I can see the light of understanding starting to dawn in your brains. So let's just do this. If a line's coming off like this, where does it have to terminate? A negative charge. Are there any negative charges around to terminate it on? Except at infinity. Ah, okay. So there's another line that wants to come off like this, right? What can't those two lines do? Touch, right? So they don't exist. Okay? The rule is, right, they can't cross or touch, and so there is no line that connects between these two. Okay? Instead, we can draw lines that start off at an angle, they'll come up, and they'll kind of do that with each other. And then these will kind of do that. And I'm being sloppy, but you're getting the general gist, right? Something like that, right? But do you see that there's a space here where there's no electric field? So, if we drop, positive charge right there, equidistant between the positive charges, what's it going to do? It's going to stay there. If It's an unstable equilibrium. So if it's just a little bit high, it'll go whoop, right? If it's a little bit low, it'll go whoop. They make those sounds. Really. But if it's exactly in the middle, where no electric field line can exist, what's the force on it? Zero. If we look at Coulomb's law, the charge on the left will want to push it that way, the charge on the right will want to push it that way, and those two would cancel out because the distances are the same and the magnitudes of the charge are the same. If it's a negative charge sitting right here, well, it gets pulled that way, it gets pulled that way, and then it just stays there, right? Because it's equally pulled. The density of lines, like how close lines are together, tells you the magnitude of the force. Like the closer lines are together, the more force the charge will experience. So a charge way out here is experiencing less force than, say, a charge right there. All without math. Now, of course, we're going to do some math. Right? Okay? We're going to do some math. But let me show you a video that is an attempt at visualizing this. So the trick here is that, or the problem, not the trick. The problem is that the screen and the board and everything else, your piece of paper, is a two-dimensional surface, right?
Yes.
Is the field two-dimensional? No.
Anywhere in the vicinity of an electric charge, a small test charge experiences a force. If it's due to only one charge, the pattern of forces detected by the test charge is simple. The pattern's more complex with the opposite charges. Or for two charges of the same sign.
Do you like the trippy music?
And more complex still, for more complicated arrangements. But in any case, here's the point. Even if the test charge isn't there to feel it, the pattern of forces can be imagined to exist everywhere in space. This is the essence of the idea of the field. And although Faraday only imagined it, the field can also be expressed mathematically.
See how 3D it is? And of course, there could be an infinite number of these vectors, right? We don't have time to draw them all. Okay, don't panic. Do not panic. Don't panic. Why are they going to panic? Don't panic!
Force that acts on a test charge at each point in space is equal to the test charge times a quantity due only to the other charges. That quantity is the electric field.
What's the big squirrely E?
Sigma sum.
Yeah, it's a sum, right? And if this were physics 4B, we would turn that sum into a, nope, big S, integral. But we're not going to do that. So I said, don't panic.
As Faraday imagined it, this something would be lines or tubes, each one capable of applying a force to any charge in its path. These lines of force would begin only on positive charges and end only on negative ones. And they would flow smoothly through space, never crossing or tangling. No matter the configuration, the charges would have a characteristic pattern of lines. The force they applied would be strong near the charges where the lines are crowded together, and weak far from the charges where the lines are farther apart. The ability to apply a force resides at each point in space, and the force arises from the intensity of lines, regardless of the location of the charges that create them.
So on that picture right there, where is the charge? Left or right side of the screen? What you left, right? We don't have the arrows on here, but the charge would be somewhere on the left. Even if we can't see it, right? We know there's got to be charge over there somewhere because the lines are kind of closer together over there, right? And then we're moving away from the charge as we go to the right across that screen. So I hope that that just kind of helped you see that there is a three-dimensionality to the electric field. We're still cheating a little bit by only doing things in 2 dimensions. So let's do another quiz. Let's see how you're doing. Quiz sheets. 18.5, 18.6. Two points. Oh, yeah. See, it's a good thing you always put reminders in. So what we're going to do is we're going to do an electric field problem now. Okay? And this is a slightly different geometry, right? But they're asking us to find the electric field at the origin. What is the electric field right there? Okay? And I'm going to erase my little E question mark because I'm going to need to be able to draw some stuff. And I don't want it to get in the way. So so now what we're going to do, I'm going to show you the calculation. You can draw all those field lines and stuff like that, but actually it's going to help less than the method I'm going to show you right now. So this is more of a sort of a modern mathematical approach, analogous to the force one we did earlier today. Only now we're going to run the calculation in terms of electric field. Hopefully it'll be easier. So big picture, the electric field at the origin is going to be the overlap of the electric field coming from charge 1 plus the electric field coming from charge 2. Whatever those fields, where they're starting, where they're ending, whatever's going on, there's an electric field magnitude at the origin at some location in space. And we're going to find that electric field magnitude and direction by looking at the fields individually from the 2 charges and then adding them together. Yes?
What's the arrow on top of the E?
It's a vector. Yeah, electric fields are vectors because they involve forces. Remember, an electric field is the force divided by a test charge? So technically a vector. Okay. I hope already you can see that it's gotten simpler just in the symbols. Do you see how there's only one number on the electric field? It's not force, was it force 2-1 or force 1-2 or It's just the electric field from charge 1 and the electric field from charge 2. Nice. Okay. So, since we're adding vectors together, what's the overall approach? What are we going to have to find? Components, right? We got to find the magnitude, we got to find the components, we got to do all the x components, we got to do all the y components. Like the last problem we did, because even though this is electric field, it's still a vector. Okay. So, should we tackle the directions first? Like we did last time? Okay. Let's look at charge number 1. Charge number 1, positive or negative? That's a positive charge, right? Charge number 2, positive or negative? Positive also. Okay. So, what direction does the electric field from charge number 1 point if we're sitting at the origin? You can either try to imagine the field line coming off of charge number 1, or you can just put a positive charge here, and because remember, test charges are positive. You put positive, positive, so which way is it going to be? Away, right? So the field line, if you want to do field line, it would just come off like this and go like that. I'm ignoring the fact that charge 2 even exists right now, right? Okay, just looking at charge 1. And so I would just, okay, it goes like that. So at this point, it's got to go that way, doesn't it? So I'm going to go ahead and draw an actual vector there. I'll use green. No, I won't because I already used green. We'll use red. So this is the electric field from charge number 1. It points away from charge number 1. Remember, field lines go away from positive charges and toward negative charges. Okay, since charge 2 is a positive charge, what direction does the electric field point? Away. And what direction would that be, like in terms of x and y? Negative y. So we'll do blue, come down like that. Here is the electric field from charge 2.
Why, if it's a positive test charge, why wouldn't they repel?
They are. That is a repulsion away from that charge.
Oh, because the test charge is getting pushed away.
Yeah.
Not.
Yeah.
The test charge is always positive.
Yeah. But you don't have to worry about test charges either. You can just go towards and away, right? Away from positive. Like, just to practice here real quick, if we were up here, which way would away be for charge 2? It'd be up, right? What direction would away be for charge 1? Something like that, right? Okay? So you can do that with any charge. Just isolate the charges by themselves. Don't try to do the whole field together, right? Do them one at a time, because mathematically there are vectors, and vectors can add together in space. Okay, so we have the directions. We know what we need to do. So let's calculate what the electric field magnitude is going to be. So remember, it's KQ over R squared is the magnitude. But what Q do we put in? Is it the charge of the test charge? No. It's just the charge of the charge that's making the field in the first place, right? And what charge is making electric field 1? Q1. It's like, I love this. 9 times 10 to the 9 times Q1, 3.5 times 10 to the minus 9, because that's a nano right there. All divided. And how far away is charge number 1 from the origin? 0.5 meters. 50 centimeters, 0.5 meters. And we got to square it. And I don't know why I wrote the meters in there, but I did. So when I got 126. Oh, and units for the electric field? Nope. It's a force divided by a charge. A Newton per Coulomb. All right, and then let's do electric field 2. 9 times 10 to the minus 9. Those are supposed to be minuses. And then it's 5. No, oh, Jesus. See how happy I got with putting minuses on stuff? That one's positive. The other one's negative. Oh, Ben Franklin. Okay, and how far away is E2? Sorry, how far away is charge 2 from the origin? 0.25 meters. Square that. And when I did that, I got 720 newtons per coulomb. Okay? So, x and y components of E1. This should require no thought. This is EX. Right? E1 points horizontally in the positive x direction, right? So, what about EY? E2. E2y, right, is going to be negative 720. Why negative? Because it points down, right? Okay. So the 126 is positive. because it's pointing to the positive x. Okay, so now I know the components. I add x and x, y and y. Well, that's pretty easy, because 126 plus 0 is, and 0 plus negative 720 is, so, right, we've got it, right? So E at the origin x component is 126, and E at the origin y component is negative 720. So which way does this electric field point if it has a positive x and negative y component? It points somewhere down here, which looks good for our diagram, doesn't it? Okay. And then if I want to know the magnitude, that 731 newtons per coulomb. And then the angle, the word that works for a lot of stuff. I got negative 80 degrees out of the inverse tangent. Why are we adding 360? Because we're in the fourth quadrant, and I cleverly erased my trick up here. Plus 360 gives me 280. So there's my angle, there's my magnitude. What would you rather do, electric field or Coulomb's law? Right? Okay. So not only was it a brilliant, like, imaginative model, but as other physicists came along and applied the mathematics to this model, they came up with a simpler way mathematically of dealing with charges, right? So that's the power of the electric field. And in modern physics, in everyday physics, when physicists are talking about charges, we are not talking about Coulomb's law. We talk about electric field instead. We understand, know, and realize that Coulomb's law is under the hood, right? It's always there because electric field is a force divided by a test charge. So it's in there. This is just a simpler expression, more powerful conceptual framework that allows us to work in there. We can find the force on a charge at the origin now. If we put, say, a positive charge at the origin, which way would it go? It would go into the fourth quadrant, right? Why? Because that's where the electric field is pointing, right? Remember, a positive charge would follow the electric field. How would we calculate the force on that charge? No, not Coulomb's law. We know the electric field. And so we can take this definition, right, and rearrange it to find a force. If I put, say, a 10 nanocoulomb charge at the origin, I could just do 10 times 10 to the minus 9 times whatever my electric field is, 731, and I would get the force on that charge. So even if we do need to know the force on the charge for any reason, any self-respecting physicist who's not insane, and we're all a little insane, would calculate the electric field first and then just multiply by the amount of charge that happens to be sitting there to find the force. It's just what's easier mathematically, and it's even easier visually. We'll come back to electric fields inside conductors because we've got to talk about something else. There is a portion of this chapter called Gauss's law that we are actually going to skip. I did this last semester, I'm going to do it this semester, and it worked. We're going to come back to the ideas of Gauss's law when we get into magnetism. But for now, it's not worth it to confuse you with what Gauss's law and flux and stuff is. We will circle back to this in the next unit, okay? It also, I spent too much time today and I'm looking for stuff to cut. So we're done with chapter 18. You should be able to do all your chapter 18 homework. I hope I took the Gauss's law problem off. Remind me if I didn't. When's chapter 18 homework due? Is it not this Saturday,
No,
right?
next Saturday.
Good. All right, good. So Monday, what's happening? Right. Monday, what's happening? Nothing. It's a weekend, right? Or a holiday. So next Tuesday and Thursday is chapter 19. Get started. Do your chapter 18 homework. Don't put it off. It's hard. Get ready for chapter 19 with terminology and all that sort of stuff. Lab is due Tuesday.
And then the times for Friday is just all day, or?
7 to 1. If I don't see you, have a great 3-day weekend.